Hello everyone. Today we'll study algebraic properties of matrices. First of all, let me introduce properties of matrix arithmetic. Let A, B, C be matrices, and let K and L be scalars. Assume all following operations are well defined. Then we have the following properties. First property, A plus B, matrices A plus B equal to B plus A. That's called the commutative law of matrix addition. Next, matrix A plus B plus C equal to A plus B plus C. That's called the associative law of matrix addition. Next, matrix A times B times C equal to A times B times C. That's called the associative law for matrix multiplication. Next, matrix A times B plus C equal to AB plus AC. That's called a left distributive law. A times B plus C equal to AB plus AC. That's called a left distributive law. Next, matrix A plus B times C equal to AC plus BC. Here we distribute C to each of them. That's called a right distributive law. Here I distribute C to each of them. That's called a right distributive law. Here, be very, very careful. When we distribute C to A, I must write A first. I must write A on the left side, C on the right side. When I distribute C to B, I must write B on the left side, C on the right side. Don't change the order. When we distribute, don't change the order. C stay on the right side. And for the left distribution, A stay on the left side. For the left distribution, A stay on the left side. I get AB plus AC. For the right distribution, C stay on the right side. I get AC plus BC. Next, scalar K times A plus B equal to KA plus KB. Here I distribute scalar K to each of them, to each matrix. Next, scalars K plus L times A equal to KA plus LA. Here I distribute matrix to each scalar. I get KA plus LA. Next, scalar K times LA. When we have two scalar here, K times LA, I can multiply scalar together. I get KL times matrix A. I can multiply scalar together first. I can multiply K times L first, and then times matrix A. Next, scalar K times AB. If there's a scalar multiplied to a product of matrix, I can multiply the scalar to the first matrix and then times the second matrix. Or I can multiply the scalar to the second matrix first and then take the first matrix times the result. Answer will be the same. Those are the properties of matrix arithmetic. If we want to prove these properties, we need to write down some general matrix. And to see that the left side equal to the right side. For example, if we try to verify the first one, try to prove the first property, we let A equal to, assume A is m by n matrix. So assume A is A11, A12, A1m, A1n. A is n columns. A21, A22, A2n. Then AM1, AM2, AMN. Let A be an m by n matrix. In order to add A and B together, B must have the same size. Let B be another m by n matrix. So B is B11, B12, B1n. B has n columns and m rows. B21, B22, B2n, BM1, BM2, and BMN. Then try to add A, B together to the left side. Take A plus B. I get A11 plus B11 at the corresponding entries. A12 plus B12, then A1n plus B1n. Next, A21 plus B21, A22 plus B22, and then continue A2n plus B2n. Then in the last row, we have AM1 plus BM1, AM2 plus BM2. And last entry here is AMN plus BMN. That's the left hand side. That's the left hand side. Then compute on the right hand side. B plus A. B plus A. Add the corresponding entries. Now here, B comes first. Add the corresponding entries. Here, B comes first. We get B11 plus A11, B12 plus A12, B1n plus A1n, B21 plus A21, B22 plus A22, B2n plus A2n, and BM1 plus AM1, BM2 plus AM2, and BMN plus AMN. Here, all entries are real numbers. So real numbers, A11 plus B11 is the same as B11 plus A11. They are all real numbers. Therefore, here I prove A plus B equal to B plus A. And do the same thing for the rest. We set the matrices first, and then try to verify. Left side equal to the right side. That's the proof for these properties. So I leave the rest of the proof for you. Now, we have these properties for matrices, but be very, very careful. In general, for matrices, A times B doesn't equal to B times A. In general, A times B doesn't equal to B times A. However, if there exist matrices A and B with AB equal to BA, that's a special case. Then we say matrices A and B, they are commute. A and B commute. If AB equal to BA, then we say matrices A and B commute. That's a special case. Next, let me introduce the zero matrix. In a matrix, if all its entries are zero, then this matrix is called a zero matrix. Those are examples of zero matrix. If all entries are zero, those matrices are called zero matrices. Note, in general, we use zero represent zero matrix. But if it's important to emphasize in the size, then we write 0 m by n to represent a m by n zero matrix. For example, if we try to emphasize the size for this matrix, I write 0, 2 by 2. This is a 2 by 2 matrix. It has 2 rows and 2 columns. This can be represented as 0, 4 by 2. This is a 4 by 2 matrix. It has 4 rows and 2 columns. This matrix can be written as 0, 1 by 4. It has 1 row and 4 columns. This matrix can be written as 0, 5 by 1. It has 5 rows and 1 column. This 0 can be written as 0, 1 by 1. This is a 1 by 1 matrix. Next, let me show you some properties about zero matrix. Let A be a matrix and let K be a scalar. Then we have the following properties. First property, A plus 0 is equal to A. This 0 is a zero matrix. This is not number 0. This is a zero matrix. We cannot add a number to a matrix. We must add a matrix to a matrix. So A plus 0, this is a zero matrix. A plus a zero matrix equal to A. And same thing, zero matrix plus A equal to A. Part B, it says A minus zero matrix equal to A. Part C, it says A minus A. That's the same as A plus negative A. That equal to 0. This 0 is a zero matrix. This is not number 0. This is a zero matrix. When we add two matrices, the answer is always a matrix. So A minus A or A plus negative A always equal to the zero matrix. Part D, 0 times A is 0. Here, this 0, it could be a 0 matrix, or it could be number 0, it could be a scalar 0. If this is a 0 matrix times A is another 0 matrix. Assume the size match. A 0 matrix times a matrix A equal to a 0 matrix. This 0 could be a scalar. This 0 could be a scalar. A scalar 0 times the matrix. That means we distribute 0 to every entry in A. I get 0 matrix. So in both cases, 0 times A is always 0. If this 0 is a 0 matrix times A, assume the size match. 0 matrix times A is another 0 matrix. If this is a scalar, 0 times A is also a 0 matrix. For example, assume the size match. That's a 2 by 3 0 matrix. For example, assume A. Assume this is matrix A. This is a 3 by 2 matrix. When we multiply these two matrices, that's a 0 matrix times A. I use row times column. First row times first column is 0. First row times second column is 0. Second row times first column is 0. Second row times second column is 0. I got a 0 matrix. That's a 2 by 2 matrix. So that's the first case. If this 0 is a 0 matrix, 0 matrix times A, that's another 0 matrix. If this 0 is a scalar, then 0 times A when we have 0 times A, we distribute 0 to each entries. We distribute zeros to each entry in matrix A. 0 times 1 is 0, 0 times 2 is 0, 0 times 3 is 0, 0 times 4 is 0, 0 times 5 is 0, 0 times 6 is 0. We got another 0 matrix. So if this 0 is a scalar, 0 times A equal to a 0 matrix. So it works for both cases. Part E. If a scalar K times A equal to 0, then either K0 or A0. If scalar K times A is 0, then either K0 or A0. Now, let's try to prove these properties. For properties A, B, C, D, it should be simple. We let A be an n by n matrix equal to A11, A12, A1n, A21, A22, A2n, then AM1, last row AM1, AM2, AMN. Let A be an arbitrary n by n matrix. Then we try to verify on each equation, try to verify left side equal to the right side. Left side equal to the right side. Do the same thing for A, B, C, D. It should be simple. So I'll leave the proof A, B, C, D for you. Part E looks harder. I'll prove here. I'll prove part E here. So for part E, we first of all assume K times A is 0. We try to prove either K0 or A0. So assume K times A is 0. Let A be this matrix. Then if I take K times A, what do I get? If I take K times A, what do I get? If I take K times A, I multiply K to each entry here. I get KA11, KA12, KA1n, KA21, KA22, KA to N, KAM1, KAM2, and KAMN. Since KA is 0, then every entry here must be 0. Since KA is a 0 matrix, then every entry in the matrix must be 0. Then K times Aij equal to 0 for all I between 1 and N. J I between 1 and M, J between 1 and N. We try to prove either K is 0 or A is 0. If K is not 0, since Kaij is 0, then Aij must be 0. Since Aij is 0 for all I and j, then matrix A must be 0. Since Aij is 0 for all I and j, then matrix A must be a 0 matrix. Hence A is 0. So let's complete the proof. Either K is 0, then make Kij equal to 0, or K is not 0, then make A equal to 0. Let's complete the proof. Next, let me show you two rules which are true for real numbers, but not true for matrices. Let A, B, and C be real numbers. Then we have the following rules. First rule says, assume A is not 0. Assume A is not 0, then AB equal to AC implies B equal to C. That's called cancellation rule. I can divide both sides by A. Since A is not 0, I can divide both sides by A. I get B equal to C. That's called cancellation rule. This rule is true for real numbers. Another rule says, if A times B is not 0, if A times B is 0, if A times B is 0, then either A is 0 or B is 0. If the product of two numbers equals 0, then either A is 0 or B is 0. These two rules are true for real number, but they are not true for matrices. However, the above rules the above two rules are not true for matrices in general. The above two rules are not true for matrices in general. In order to show a rule is not true, we try to show a counterexample. That means we try to find an example, then make a hypothesis true, but the conclusion false. So let's try to find a counterexample for each of them. For the first rule, let's find a counterexample. Let matrix A equal to 1, 2, 2, 4. Let B equal to 1, 3, 2, 0. And let C equal to 3, 1, 1, 1. We try to show the hypothesis is true, but the conclusion is false. Let's first of all find AB and AC. We try to show that AB equal to AC. Then what's AB here? For AB, we use row times column. Row times column. 1 times 1 plus 2 times 2, that's 5. Next, row times column. 1 times 3 is 3. 2 times 0 is 0. 3 plus 0 is 3. Next, row times column. 1 times 2 is 2. 4 times 2 is 8. 2 plus 8 is 10. Next, row times column. 2 times 3 is 6. 4 times 0 is 0. 6 plus 0 is 6. That's AB. How about AC? Same thing. Use row times column. AC, row times column. 1 times 3 is 3. 2 times 1 is 2. 3 plus 2 is 5. Next, row times column. 1 times 1 is 1. 2 times 1 is 2. 1 plus 2 is 3. Next, row times column. 2 times 3 is 6. 4 times 1 is 4. 6 plus 4 is 10. Next, row times column. 2 times 1 is 2. 4 times 1 is 4. 2 plus 4 is 6. So here we can see that AB equal to AC. But B doesn't equal to C. But B doesn't equal to C. So here, A is not 0. AB equal to AC, but B doesn't equal to C. So the first rule is not true for matrices. Therefore, assume A is not 0. AB equal to AC doesn't imply B equal to C. So the first rule is not true for matrices. For the second rule, do the same thing. We try to find a counterexample. Find an example, then make the hypothesis true, but the conclusion false. So let's find another example. Let A be the matrix 1, 2, 3, 6. And B equal to matrix 2, negative 4, negative 1, 2. Then, what's A times B? For A times B, we use row times column. Row times column. 1 times 2 is 2. 2 times negative 1 is negative 2. 2 plus negative 2 is 0. Next, row times column. 1 times negative 4 is negative 4. 2 times 2 is 4. Negative 4 plus 4 is also 0. Next, row times column. 3 times 2 is 6. 6 times negative 1 is negative 6. 6 plus negative 6 is 0. Next, row times column. 3 times negative 4 is negative 12. 6 times 2 is 12. Negative 12 plus 12 is 0. So here, AB is a zero matrix. So here, AB is a zero matrix, but A is not 0, B is not 0. A is not zero matrix, and B is not zero matrix. That's a counterexample. Then make a hypothesis true, but a conclusion false. So this rule is not true for matrices. So the second rule is not true for matrices. Therefore, AB equal to 0 doesn't imply A equal to 0 or B equal to 0. So these two rules are not true for matrices. They are true for real numbers, but not true for matrices. Next, let me introduce identity matrix. In a square matrix, if the entries are ones in the main diagonal and zeros elsewhere, then this matrix is called identity matrix. Here are some examples of identity matrix. If there are ones in the main diagonal and zeros elsewhere, this is identity matrix. If there are ones in the main diagonal and zeros elsewhere, this is identity matrix. If there are ones in the main diagonal, zeros elsewhere, this is identity matrix. And that's a special case. There are ones in the main diagonal, zeros elsewhere. This is identity matrix. Note, in general, we use capital letter I to represent identity matrix. But if it's important to emphasize the size, we use I sub n, to represent m by n identity matrix. For example, this is a 4 by 4 identity matrix. We can represent this using I4. This is a 3 by 3 identity matrix. It can be represented using I3. This is a 2 by 2 identity matrix. It can be represented using I2. And this is a 1 by 1 identity matrix. It can be represented using I1. Next, let me show you a property about identity matrix. Let A be a m by n matrix. Then A times In equal to A. And Im times A equal to A. In order to multiply the matrix, the size must match. If A is a m by n matrix, I must be a m by n matrix. The number of columns in the first matrix must be the same as the number of rows in the second matrix. That's why I use In here. And same thing, since A is a m by n matrix, I must be a m by n matrix because the rows in the second column must be the same. The rows in the second matrix must be the same as the columns in the first matrix. So here I use In, here I use Im. The proof of this property is simple. We first of all set up general m by n matrix A, like this. We first of all set up general m by n matrix A. Then take A multiplied by In, which will get A. And similarly, take Im multiplied by A, which will get A. I'll left the proof for you. This proof should be simple. I'll left it for you. Next, let me show you a theorem. Let A be an m by n matrix, and let R be the reduced row echelon form of A. Here, REF stands for reduced row echelon form. Then, either R has a row of zeros, or R is an identity matrix. Let's prove it. Since matrix A is m by n, and R equal to the reduced row echelon form of A, then R must have the same size as matrix A. Since R is the reduced row echelon form of A, R must have the same size as A. Then we know that R has n rows and n columns. Since R is a reduced row echelon form of A, R must have the same size as matrix A. Here we try to prove either R has a row of 0 or R is an identity matrix. We know that for any matrix, either it has a row of 0 or it doesn't have a row of 0. There's only two cases. Either it has a row of 0 or it doesn't have a row of 0. If R has a row of 0, then we are done. We're done with the proof. So let's consider if R doesn't have a row of 0. If R doesn't have a row of 0, then what do we get? If R doesn't have a row of zeros, then on each row, if R doesn't have a row of 0, then on each row, there is a non-zero leading entry. If R doesn't have a row of zeros, then on each row, there must exist a non-zero leading entry. Since R is in a reduced row echelon form, then the non-zero leading entry on each row must be 1. They are called leading ones. Since R is in the reduced row echelon form, then the non-zero leading entry on each row must be 1. Therefore, there's a leading 1 on each row. Therefore, there's a leading 1 on each row. Also, since R is in a reduced row echelon form, all entries above and below leading 1 must be zeros. The entries all entries above or below leading 1 must be zeros. That means on each column there's exactly 1 leading 1. It won't be 2 leading 1 on the same column. On each column there's exactly 1 leading 1. And all the entries above below leading 1 must be 0. So there exists exactly 1 leading 1 on each column. And all other entries are 0. since R is in the reduced echelon form, the leading ones on the upper row are closer to the left. The leading ones on the upper row are closer to the left. Then all leading ones must locate on the main diagonal. All leading ones must locate on the diagonal, since all other entries are 0. Since all other entries in R are 0, then R must be an identity matrix. Hence, R equal to In, because R is n by n matrix. That complete the proof. Either R has a row of 0 or R doesn't have a row of 0. If R doesn't have a row of 0, then R is an identity matrix. That complete the proof. Next, let me introduce inverse matrix. Let A be a square matrix if there exists a matrix B of the same size, such that AB equal to I and BA equal to I. Then we say matrix A is invertible, and B is called inverse matrix of A. For any square matrix A, if there exists matrix B such that AB equal to I and BA equal to I, then we say A is invertible. B is called inverse of A. Note, if there does not exist such B, then we say A is not invertible, or we say A is singular. For any matrix A, if there exists a B such that AB equal to I and BA equal to I, then we say A is invertible. If there does not exist such B, then we say A is not invertible, or A is singular. Singular means not invertible. Also, if A is the inverse of B, then B is also inverse of A. So in this case, we say A and B, they are inverse of each other. In this case, we say A and B, they are inverses of each other. If A is the inverse of B, then B is also inverse of A. In this case, we say A and B, they are inverses of each other. Next, let's look at an example. Let A be the matrix 2, -3, 3, 5, and let B be the matrix 5, -3, 3, -2. Show that A and B are inverses of each other. In order to show A and B they are inverse of each other, we must show two things. We must show AB equal to I and BA equal to I. Show two things. Show A times B equal to I and B times A equal to I. So that's how we show A and B is identity, is the inverse of each other. So let's first of all, let's do AB. A times B, what do we get? Matrix A times B. Use row times column. Row times column. Then we copy the matrix first. That's matrix A. That's matrix B. Use row times column. Row times column. 2 times 5 is 10. Negative 3 times 3 is negative 9. 10 plus negative 9 is 1. Next entry, row times column. 2 times negative 3 is negative 6. Negative 3 times negative 2 is positive 6. Negative 6 plus positive 6 is 0. Next entry, row times column. 3 times 5 is 15. Negative 5 times 3 is negative 15. 15 plus negative 15 is 0. Next entry, row times column. 3 times negative 3 is negative 9. Negative 4 times negative 2 is positive 10. Negative 9 plus positive 10 is 1. This is identity matrix. So A times B equal to I. Next, let's try to multiply BA. We need to show AB equal to I and BA equal to I. We need to show both of them. Next, let's do B times A. Write matrix B first. Matrix B is 5, negative 3, 3, negative 2. Matrix A is 2, negative 3, 3, negative 5. Take matrix B times A. Here use row times column. Row times column. 5 times 2 is 10. Negative 3 times 3 is negative 9. 10 plus negative 9 is 1. Next, row times column. 5 times negative 3 is negative 15. Negative 3 times negative 5 is positive 15. Negative 15 plus positive 15 is 0. Next, row times column. 3 times 2 is 6. Negative 2 times 3 is negative 6. 6 plus negative 6 is 0. Next entry, row times column. 3 times negative 3 is negative 9. Negative 2 times negative 5 is 10. Negative 9 plus 10 is positive 1. That's also identity. Since AB equal to I, BA equal to I, then we can say A and B, they are inverse of each other. So, matrix A and B are inverse of each other. Next, let me introduce uniqueness of inverse matrix. Let A be a square matrix. If matrices B and C are both inverse of A, then B equal to C, which means if A has two inverse B and C, then they must be the same. If A has two inverse, then they must be the same. Let's prove it. Since B and C are inverse of A, then we have AB equal to BA equal to I, and AC equal to CA equal to I. AB equal to I. For AB equal to I, if I multiply both sides by C, I have C times AB equal to C times I. On the left side, we can apply associative law. On the left side, apply associative law. It can be rewritten as C times A times B. On the right side, since I is identity matrix, C times I equal to C. On the left side here, C times I, C times A equal to I. On the left side, C times A equal to I. So I get IB equal to C. Since I is identity matrix, so I times B equal to B. Let's prove that B equal to C, which means if A has inverse, then it must be unique. If A has an inverse, then it must be unique. That complete the proof. Note, based on the above theorem, we know that inverse of A is unique. So if A has an inverse, if A has an inverse matrix, then it's called the inverse of A. Since it's unique, there's only one. It's called the inverse of A. Denoted by A inverse. It's read A inverse. It's read A inverse. Hence, we have A times inverse of A equal to identity, and inverse of A times A equal to identity. Be very, very careful. Inverse of A doesn't equal to 1 over A. There's no matrix division. We can't divide a number by a matrix. Inverse of A doesn't equal to 1 over A. We cannot divide a number by a matrix. Be very, very careful. Inverse of A doesn't equal to 1 over A. We cannot divide a number by a matrix. Keep it in mind. Inverse of A doesn't equal to 1 over A. We cannot divide a number by a matrix. Next theorem. Let A be an invertible matrix. If AB equal to AC, then B equal to C. This is a cancellation rule. We know that for matrices, cancellation rule is not true in general. However, if A is invertible, then the cancellation rule is true. Let's prove it. Since A is invertible, then inverse of A exists such that A times inverse of A equal to identity. Inverse of A times A equal to identity. Start from AB equal to AC. We try to prove B equal to C. First of all, I can multiply both sides by inverse of A. I get inverse of A times AB equal to inverse of A times AC. Now, for matrix equation, if I multiply both sides by another matrix, it must be multiplied on the same side. If I multiply inverse of A on the right side, I must multiply inverse of A on the right side from the other side. Then it must be multiplied on the same side. I cannot multiply one on the left side, the other on the right side. If I write inverse of A times AB equal to AC times inverse of A, if I multiply one on the left side, one on the right side, that's not true. I must multiply inverse of A, either both on the left side or both on the right side. I cannot multiply one on the left, one on the right. For matrix equation, when we multiply a matrix equation by another matrix, it must be multiplied on the same side, either both on the left side or both on the right side. Here I multiply C, both on the left side. Here I multiply inverse of A, both on the left side. Next, apply associative law. Apply associative law. This can be rewritten as inverse of A times B. And this can be rewritten as inverse of A times C. And we know that inverse of A times A is identity. You get identity times B equal to identity times C. And we know that identity times B is B. Identity times C is C. So I prove if AB equal to AC, then B equal to C. So if A is an invertible matrix, then the cancellation rule is true. Next, let me show you to find the inverse of a 2 by 2 matrix. Let A be a 2 by 2 matrix, A, B, C, D. Matrix A is invertible if and only if AD minus BC is not 0. A is invertible if and only if AD minus BC is not 0. If A is invertible, then inverse of A is 1 over AD minus BC times the matrix D, negative B, negative C, and A. This matrix can be obtained by interchanging AD and then change the sign for BC. Interchange AD, then change the sign for BC. I got this new matrix here. I'll show you the proof of this theorem in chapter 2. Right now, let's assume this is true. Assume this theorem is true. Even though I don't prove it here, but at least we can verify this is the inverse of A. How do we verify this is the inverse of A? In order to verify this is inverse of A, we need to show two things. We need to show A times inverse of A equal to identity, and inverse of A times A equal to identity. We need to show A times inverse of A equal to identity, and inverse of A times A equal to identity. So let's multiply. A times inverse of A. Matrix A is A, B, C, D times inverse of A. That's 1 over AD minus BC times the matrix D, negative B, negative C, and A. That's a matrix times the scalar times the matrix. Here I can pull out the scalar 1 over AD minus BC. Then multiply the matrix A, B, C, D times D times negative B times D, negative B, negative C, and A. Let's multiply the matrices first. If I multiply the matrices, take row times column, AD times AD plus B times negative C. That's negative BC. Next, row times columns. A times negative B is negative AB. B times A is plus AB. Next, row times columns. C times D is CD. D times negative C is negative CD. Next, row times columns. C times negative B is negative BC. D times A is AD. Then simplify. I get 1 over AD minus BC. AD minus BC. Negative AB plus AB is 0. CD minus CD is also 0. Negative BC plus AD can be rewritten as AD minus BC. Then multiply the scalar to the matrix. When I multiply the scalar to the matrix, this times this is 1. They have the same denominator. The numerator and denominator is the same. I get 1. This times 0 is 0. This times 0 is 0. This times this. They are reciprocal. I get 1. This is identity matrix. And then next, we need to verify. Inverse of A times A is identity. I leave the second part for you. Take the inverse of A times A. You should also get identity. And I leave the other part for you. So that's how we find an inverse matrix for 2 by 2 matrix. Note, the expression AD minus BC, this expression AD minus BC, is called a determinant of A. This expression AD minus BC is called determinant of A, denoted by DET of A. I'll explain to you what's determinant in chapter 2. Right now, let's assume we know this formula is called determinant of A. This formula AD minus BC is called determinant of A. I'll explain to you what's determinant in chapter 2. Right now, let's just assume we know this expression AD minus BC is determinant of A. It's written as DET of A. So, based on the theorem, we know that if determinant of A is not 0, the matrix A is invertible. If determinant of A is 0, then the matrix is not invertible. If determinant of A is not 0, matrix is invertible. And that's the inverse matrix of A. If determinant of A is 0, then the matrix is not invertible. If determinant of A is 0, the matrix A is not invertible. Next, let's look at an example. For each of the following matrices, determine whether it's invertible. If it's invertible, find the inverse matrix. So, in order to check if a matrix is invertible or not, we try to find a determinant. If the determinant of a matrix is not 0, then the matrix is invertible. If the determinant of a matrix is 0, then the matrix is not invertible. So let's check determinant of A. Determinant of A is AD minus BC. 4 times 3 is 12, minus 6 times 2 is also 12. 12 minus 12 is 0. If determinant of A is 0, that means A is not invertible. How about matrix B? Determinant of B is what? 3 times 6 is 18, minus 8 times 5 is 40. That's negative 22, which is not 0. So matrix B is invertible. For inverse of B, we take 1 over determinant of B. One over determinant of B times the matrix D, negative B, negative C, and A. That means I interchange the main diagonal, interchange AD, change the sign for BC. Interchange AD, I get 6, 3. Change the sign for BC, I get negative A, negative 5. And then we know that determinant of B is negative 22. I get 1 over negative 22 times the matrix 6, negative A, negative 5, and 3. Then when we have a scalar times the matrix, I distribute the scalar into the matrix. I get 6 over negative 22. That can be reduced as 3 over 11. A over 22 can be reduced as 4 over 11. On the bottom, I get 5 over 22 and negative 3 over 22. That's the inverse of B. That's how we find inverse of B. Next theorem. Let A and B be square matrices of the same size. If both A and B are invertible, then their product A times B is also invertible. And inverse of AB is inverse of B times inverse of A. So for this theorem, we need to prove two things. AB is invertible, and inverse of AB is inverse of B times inverse of A. So for this theorem, I'll first of all prove that inverse of AB is inverse of B times inverse of A. Then, if inverse of AB exists, AB is invertible. So let's prove it. I'll first of all prove inverse of AB equal to this. So in order to prove that inverse of AB is inverse of B times inverse of A. We need to show that AB times this is identity, and this expression times AB is also identity. We need to prove these two statements to show this is inverse of AB. Let's prove the first statement first. AB times inverse of B times inverse of A. By associative law, this expression can be rewritten as A times inverse A times B times inverse of B, then times inverse of A by associative law. And then B times inverse of B is identity. A times identity is A times inverse of A. A times inverse of A is identity. That's the proof of the first statement. Next, let's prove the second one. Inverse of B times inverse of A times AB. We try to prove this also equal to identity. So by associative law, this expression can be rewritten as inverse of B times inverse of A times B. And we know that inverse of A times A is identity. Inverse of B times identity is inverse of B. Inverse of B times B is identity. Since I proved both of them, that means inverse of AB is inverse of B times inverse of A. So inverse of AB is inverse of B times inverse of A. If inverse of AB exists, then AB is invertible. Hence AB, A times B, the product of AB, A times B, is invertible. Since inverse of AB exists, AB is invertible. That complete the proof. Now next, let's observe this expression here. AB inverse equal to inverse of B times inverse of A. That means if I distribute inverse, I reverse an order of matrices. If I distribute inverse, I reverse an order of matrices. Originally, A comes first, B comes after. If I distribute inverse function, inverse of B comes first, A comes after. So if I distribute inverse, I reverse an order of matrices. So keep it in mind. Note, in general, let A1, A2, AN minus 1, AN be invertible matrices. Of the same size. Then the expression A1 times A2 times AN minus 1 times AN inverse, it can be rewritten as AN inverse times AN minus 1 inverse A2 inverse times A1 inverse. If I distribute inverse, I reverse an order of matrices. So AN comes first, then AN minus 1. Last one is A2 and A1. This can be proved based on this, using mathematical induction. Here I omit the proof. So keep this idea in mind. If I distribute inverse, I reverse an order of matrices. Next, let me introduce powers of a matrix. Let A be a square matrix. We define A raised to power 0 as identity matrix. And we define A raised to power n as n factors of A multiplied together. If A is invertible, we define A raised to negative n as n factors of inverse of A multiplied together. So a raised to negative n is inverse of a raised to power n. Based on the above definition, we have the following exponential rules. A raised to power r times a raised to power s equal to a raised to the power of r plus s. And a raised to power r raised to power s is a raised to the power of r times s for all integers r and s. Those are exponential rules. Those are the exponential rules. Next, let me introduce properties of negative exponents. Let A be an invertible matrix. Let m be a non-negative integer. And let k be a non-zero scalar. We have the following properties. Part A, inverse of A is invertible, and the inverse of A is A. Part B, A raised to power n is invertible, and the inverse of A raised to power n is A raised to negative n. Part C, it says, a scalar k times A, Ka is invertible, and inverse of Ka is k raised to negative 1 times inverse of A. Here, k is a scalar, so k raised to negative 1 is 1 over k, is the reciprocal of k. A is a matrix, so A raised to negative 1, that's the inverse matrix of A. So be very, very careful here. K is a scalar. K raised to negative 1 is 1 over k. Now let's prove it. Part A is obviously. Inverse of A inverse is A. That's obviously. So I'll omit the proof of part A. Let's prove for part B and part C. For part B, we try to prove A raised to power n is invertible, and the inverse of A raised to power n is A raised to negative n. I will first of all prove inverse of A raised to power n is A raised to negative n. If inverse of A raised to power n exists, A raised to power n is invertible. So let's prove this first. In order to prove the inverse of A raised to power n is A raised to negative n, we need to prove that A raised to power n times A raised to negative n is identity. And A raised to negative n times A to the power n is also identity. So let's prove it. First one, A raised to power n times A raised to negative n. When we multiply A raised to power n times A raised to negative n, by this rule here, by the exponential rule here, I can add exponents. I get A raised to the power of n plus negative n, which is A raised to the power of 0, which is identity. A raised to the power of 0 is identity. For the other one, A raised to negative n times A to the power n, same thing. By the exponential rule here, I can add exponents. I get A raised to negative n plus n, which is also A raised to the power 0. And we know that A raised to the power 0 is identity, which means the inverse of A raised to the power n is A raised to negative n. Hence, inverse of A raised to power n is A raised to power n. Since inverse of A raised to power n exists, since the inverse of A raised to power n exists, I can say A raised to power n is invertible. Since inverse of a raised to the power n exists, we say a raised to the power n is invertible. Let's complete the proof for part B. For part C, same thing. We try to prove inverse of k times a, inverse of ka exists. We try to prove inverse of ka equal to k, inverse, try to prove inverse of ka is k raised to -1 times inverse of a. If inverse of ka exists, then ka is invertible. So for part C, in order to prove the inverse of Ka is k raised to -1 times a times inverse of a. We need to prove that Ka times k raised to -1 times a inverse of a equal to identity, and k raised to -1 times inverse of a times Ka equal to identity. Let's prove the first equation first. First equation, Ka times k raised to -1 times a inverse of a. Here, k and k raised to -1, they are both scalars. So I can pull out scalar, multiply the matrices first. If I pull out scalar, I have k times k raised to -1 times matrix A times inverse of A. K times its reciprocal is 1. K times k raised to -1. K times its reciprocal is 1. And A times inverse of A is identity matrix. 1 times identity matrix is identity matrix. Next, check the other equation. K raised to -1 times inverse of A times Ka. Here, k raised to -1 and k, they are both scalars. I can pull out scalar. What's left is inverse of A times A. And we know that k times its reciprocal is 1. Inverse of A times A is identity. 1 times identity is identity. Since I verify both equations, that means inverse of Ka is k raised to -1 times inverse of A. So inverse of Ka is k raised to -1 times inverse of A. If inverse of Ka exists, then Ka is invertible. Here I prove that inverse of Ka exists, then Ka is invertible. Let's complete the proof for part B and part C. Next, let's look at an example. Let inverse of 2a plus 3i equal to the 2 by 2 matrix 1, 3, -2, and 4. Find matrix A. So what should we do here? We try to get A by itself. What should we do here? We have 2a plus 3i. Inverse of 2a plus 3i equal to the 2 by 2 matrix 1, 3, -2, 4. How can I get A by itself? First of all, by the previous theorem, we know that inverse of A equal to A for any matrix. Inverse of A equal to A. If I apply inverse on both sides, what do I get? If I apply inverse on both sides, On the left side, inverse can cancel. We get 2a plus 3i. On the right side, how do we find inverse of this 2 by 2 matrix? For inverse of 2 by 2 matrix, if A is A, B, C, D, its inverse is always 1 over the determinant AD minus BC. Then for the matrix, interchange the main diagonal, we get DA, interchange DA. Change the sign for BC, negative B, negative C. That's how we find inverse for 2 by 2 matrix. So for this 2 by 2 matrix, use this formula. 1 over AD minus BC. 4 minus negative 6. 4 minus negative 6 is 4 plus 6. Then interchange AD, I get 4, 1. Change the sign for BC, I get negative 3, positive 2. That's 1 over 10. 1 over 4 plus 6 is 1 over 10. Now, how do I get A by itself? In order to make it simple, to make a calculation simple, I can multiply both sides by 10, make it easier. I can multiply both sides by number 10. So I get 10 times 2a plus 3i. I try to avoid fractions. I multiply both sides by 10. If I distribute 1 over 10, it will be fractions here. I try to avoid fractions, so I multiply both sides by 10. So 10 times 2a plus 3i equal to 4, negative 3, 2, and 1. Then I can distribute 10. If I distribute 10, I get 20a plus 30i equal to the matrix 2, negative 3, 2, 1. Then I can subtract 30i from both sides. I get 20a equal to 4, negative 3, 2, 1 minus 30i. What's I here? This is a 2 by 2 matrix, so I must also be 2 by 2 matrix. This is a 2 by 2 matrix, so I must also be a 2 by 2 matrix. Because if the sum of two matrices is 2 by 2, both matrices must be 2 by 2. If the sum of two matrices is 2 by 2 matrix, then both matrices here must be 2 by 2. So I must be a 2 by 2 matrix. A 2 by 2 identity matrix is 1, 0, 0, 1. That's 30i. Then simplify the right side. 4, negative 3, 4, 1. Distribute negative 30. Distribute 30 here. I get 30, 0, 0, 30. Then subtract. 4 minus 30 is negative 26. Negative 3 minus 0 is negative 3. 2 minus 0 is 2. 1 minus 30 is negative 29. And then I multiply both sides by 1 over 20. So A equal to negative 26 over 20 is negative 13 over 10. Negative 3 over 20 is negative 3 over 20. 2 over 20 is 1 over 10. Negative 29 over 20 stays the same. That's negative 29 over 20. That's matrix A. Next, let me introduce matrix polynomial. Let A be a square matrix, and then the polynomial P of x equal A0 plus A1x plus A2x squared plus an times x raised to power n. Then we define the matrix polynomial P of A as P of A equal to A0 times I plus A1 times A plus A2 times A squared plus an times A raised to power A raised to power n. So for the matrix polynomial P of A, we plug in A for each x. But where does this I come from? Think of this. If there's no I here, we have A0 plus a matrix. A scalar plus a matrix is undefined. So we need to fix the problem. we can't have a0 here. We need to fix the problem. How do we fix the problem? Think of exponents. Here we have x to the power 2. X by itself means x raised to the power 1. If there's no x, we can consider x raised to the power 0. So if I plug in a, I have a squared, a raised to the power 1, and a raised to the power 0. A raised to the power 0 is an identity matrix. A raised to the power 0 is an identity matrix. That's why we have an I here. So for the matrix polynomial P of A, we plug in A for each x. If there's a constant, we take constant times I, times identity matrix. If there's a constant, take constant times identity matrix. Next, let's look at an example. Let A be a 2 by 2 matrix, 1, 2, 4, 3. And let P of x be the polynomial x squared minus 4x minus 5. Part A. Show that P of A is 0. This 0 means 0 matrix. If I plug in A into the polynomial, I got a matrix here. So this 0 is a 0 matrix. Show that P of A is a 0 matrix. So for P of A, we plug in A for each x. Plug in A for each x. I get a squared minus 4a minus 5. I cannot write 5 by itself. I must write 5i. If there's a constant, when I plug in A, if there's a constant, I take the constant times I. I is identity matrix. Then plug in. Matrix A is 1, 2, 4, 3. Matrix A is 1, 2, 4, 3 minus 5i. I is 1, 0, 0, 1. That's P of A. Now let's compute the exponent first. 1, 2, 4, 3 times 1, 2, 4, 3. What do we get? 1, 2, 4, 3 square. That means the matrix 1, 2, 4, 3 multiplied by itself. 1, 2, 4, 3. So use row times columns. Row times column. 1 times 1 is 1. 2 times 4 is 8. 1 plus 8 is 9. Next, row times column. 1 times 2 is 2. 2 times 3 is 6. 2 plus 6 is 8. Next, row times column. 1 times 4 is 4. 4 times 3 is 12. 4 plus 12 is 16. Next, row times columns. 2 times 4 is 8. 3 times 3 is 9. 8 plus 9 is 17. That's a squared. So we have 9, 8, 16, 17 minus the matrix here. Distribute 4. 4 is a scalar. I distribute 4 into the matrix. 1 times 4 is 4. 4 times 2 is 8. 4 times 4 is 16. 4 times 3 is 12. Minus, here I distribute 5. 5 times 1 is 5. 5 times 0 is 0. 5 times 1 is 5. Then let's subtract. Subtract the corresponding entries. 9 minus 4 minus 5 is 0. A minus 0 is 0. 16 minus 16 minus 0 is 0. 17 minus 12 is 5. 5 minus 5 is 0. So P of A equal to the 0 matrix. So P of A equal to the 0 matrix. That's part A. Show that P of A is 0. Part B. Use part A to write A to the power 4 in terms of A. What should we do? How can we use part A? Based on part A, we know that P of A is 0. And we know P of A is A squared minus 4A minus 5I. So A squared minus 4a minus 5i equal to 0. We try to obtain a raised to the power 4 from here. What can we do here? I can first of all isolate a square. Let's isolate a square first. So I add 4a to both sides, add 5i to both sides. So I have a squared equal to 4a plus 5i. Here I have a squared equal to 4a plus 5i. How do I obtain a to the power 4? We try to obtain a to the power 4. What can we do here? If I multiply both sides by a, what do I get? If I multiply both sides by a, I get a times a squared equal to a times 4a plus 5i. A times a squared is a cubed. If I distribute a, I get 4a squared plus 5a. If I distribute a here, a times I is a. Next, we try to rewrite everything in terms of a. So that means we don't want a squared here. So I can replace a squared with 4a plus 5i. I can replace a squared with 4a plus 5i. So a cubed equal to 4 times 4a plus 5i plus 5a. If I simplify, I have 16a plus 20i plus 5a. Then I can combine like terms. 16a plus 5a is 21a plus 20i. We try to obtain a raised to the power 4. I can continue multiply both sides by a. If I multiply both sides by a, I get a times a to the power 3 equal to a times 21a plus 20i. On the right side, on the left side here, a times a cubed is a raised to the power 4. If I distribute a, I get 21a squared plus 20a. A times I is a. But we want a to the power 4 in terms of only a. We don't want a squared here. So I replace a squared with 4a plus 5i. A raised to the power 4 equal to 21 times 4a plus 5i plus 20a. If I distribute 21, I get 84a plus 105i plus 28. Combine like terms, I get 104a plus 105i. Here I write a raised to the power 4 in terms of a. I is a constant, it doesn't count. So here I write a raised to the power 4 in terms of a. A raised to the power 4 in terms of a. I is a constant, it doesn't count. So I write a raised to the power 4 in terms of a. That's part B. Part C. Compute a raised to the power 4 using part B. So compute a raised to the power 4 using part B. Based on part B, we know a raised to the power 4 is 104 times a plus 105 times I. Matrix A is 1, 2, 4, 3. Matrix I is 1, 0, 0, 1. If I distribute 104, I get 104. 104 times 2 is 208. 104 times 4 is 416. 104 times 3 is 312. Distribute 105, I get 105. 0, 0, 105. Adding up, I get 209, 208, 416, and 417. That's a raised to the power 4. Now let's check an answer. This is a raised to the power 4. We know that a raised to the power 4 can be written as a squared times a squared. Here a squared is 9a 16 17. (9a 16 17). Let's multiply the matrices. Row times column. 9 times 9 plus a times 16. 9 times 9 is 81. A times 16 is 128. Together is 209. That's the first entry. Next, row times column. 9 times 8 is 72. 8 times 17. Is 136. 72 plus 136 is 208. Next, row times columns. 9 times 16 plus 16 times 17. 9 times 16 is 144. 16 times 17. I got 272. That's 416. Next, row times column. 8 times 16 is 128. 17 times 17 is 289. 128 plus 289 is 417. We get exactly the same answer. But using this technique to compute 8 to the power 4, we have less computation. Next, let me introduce properties of transpose. Let A and B be two matrices, and let K be a scalar. Assume all following operations are well defined. Then we have the following properties. Part A, it says, for any identity matrix I transpose is I. Part B, it says, A transpose transpose is A. Part C, it says, A plus B transpose is A transpose plus B transpose. And part D says, K times A transpose is K times A transpose. Part E says, A times B transpose is B transpose times A transpose. So, the properties A, B, C, D should be simple. For A, B, C, D, we write down the general matrix. For matrix A and matrix B, make sure their sides allow you to add or multiply. Write down general matrix for A and B. Then verify left side equal to the right side. So A, B, C, D should be simple. The only hard one is part D, is part E. Let me prove here for you. Let me prove for part E here. Let me prove for part E. For part E, in order to multiply matrix A and B, the number of columns in matrix A must be the same as number of rows in matrix B. So let A be a M by K matrix. Let B be a K by M matrix. Then we're allowed to multiply matrix A and B. And when we multiply A and B, it's a M by M matrix. So let A be a M by K matrix. Let A be an M by K matrix with row vectors R1, R2, Rm. A has M rows. Then matrix A can be written as matrix A equal to row 1, row 2, row m. Here, R1, R2, Rm, they are row vectors. They are entries in rows. Let B be a k by n matrix. With column vectors. We try to use row times column. So let B be a k by n matrix with column vectors. C1, C2. B has n columns, row times column. B has n columns, so Cn. Then matrix B can be written as B equal to C1, C2, Cn. Those are column vectors. C1, C2, Cn, they are column vectors. Then let's multiply AB. If I multiply AB, what do I get? A has row vectors R1, R2, Rm. B has column vectors C1, C2, Cn. If I multiply these two matrices, I use row times column. Use row times column, so you'll be R1, C1, row times column, R1, C2, R1, Cn in the first row, R2, C1, R2, C2, R2, Cn in the second row, then Rm, C1, Rm, C2, Rm, Cn in the last row. That's matrix A times B. What's A times B transpose? What's AB transpose? For AB transpose, I put the rows in columns. For AB transpose, put the rows in columns. So put the first row in the first column. I get R1, C1, R1, C2, R1, Cn, R2, C1, R2, C2, R2, Cn. Then put the last row in the last column. I got Rm, C1, Rm, C2, Rm, Cn. That's A times B transpose. Next, let's try to compute on the right side. B transpose times A transpose, what do we get? For B transpose, we put columns in rows. We put rows in columns, put columns in rows. So B transpose can be written as C1, C2, Cn. Now those are row vectors. Those are row vectors. For A transpose, we put rows in columns. For A transpose, we put rows in columns. R1, R2, Rn. Then multiply. What's B transpose times A transpose? What's B transpose times A transpose? Use row times column. B transpose has rows C1, C2, Cn. A transpose is R1, R2, Rn. Then take row times columns. I get C1, R1, C1, R2, C1, Rn in the first row. Second row, C2, R1, C2, R2, C2, Rn. In the last row, we have Cn, R1, Cn, R2. We have Rm here. A is from R1, R2 to Rm. It should be C1, Rm in the first row, C2, Rm in the second row, last row, Cn, Rm. If we compare these two matrices, they are exactly the same. Here for R1, C1, we can consider their dot products. We multiply the corresponding entries and add them up. Their value is exactly the same. For C1, R1, R1, C1, consider their dot products. When we apply dot product for two vectors, their value is exactly the same. We multiply corresponding entries for both row vector and column vector. We multiply the corresponding entries and add them up. They are exactly the same. Since Ri times Cj equal to Cj times Ri for all I between 1 and m, and all j between 1 and n, then we can see that these two matrices, they are exactly the same. So AB transpose equal to B transpose times A transpose. That's the proof for part E. Proof for the rest, A, B, C, D should be simple. I leave the rest for you. Next, let's try a simple example about transpose. Show that A raised to power n transpose equal to A transpose raised to power n. Let's prove it. We know that A raised to power n transpose, it can be written as A times A times A transpose. There are n factors here. By the previous theorem, we know that A times B transpose can be written as B transpose times A transpose, which means if I distribute transpose into the parentheses, I run the matrices backward. I get B transpose, A transpose. If I distribute transpose into the parentheses, I run the matrices backward. So same thing here. If I distribute transpose, I run the matrices backward. So the last matrix becomes the first matrix. I got A transpose, and so on. The second matrix becomes the second last matrix, and the first matrix becomes the last matrix. Distribute transpose, write all matrices backward, and we still have n factors here. If there are n factors of A transpose multiplied together, that's A transpose raised to power n. Let's complete the proof. Next, let's create a theorem. let A be a square matrix. If A is invertible, then A transpose is also invertible. And inverse of A transpose is A inverse transpose. Let's prove it. We first of all try to prove the inverse of A transpose is this expression, and then if the inverse of A transpose exists, A transpose is invertible. So we try to prove inverse of A transpose is this. In order to prove that the inverse of A transpose is inverse of A transpose we need to prove A transpose times this expression is identity, and this expression times A transpose is also identity. So let's prove each of them individually. Look at the first one. First one we have A transpose times A inverse transpose. What do we have here? By the last property here, if I factor transpose out, I reverse an order for these matrices. If I factor, look at expression from right to left. If I factor transpose out, I reverse an order for the matrices. So, if I factor transpose out, I reverse an order for the matrices. So I write inverse of A first, and then times A. If I factor transpose out, I reverse an order for A and inverse of A. And we know that inverse of A times A is identity. Identity transpose equal to identity itself. That's the first property. Identity transpose equal to identity itself. That's the first equation. Next, proof the second equation. The proof is very, very similar. A inverse transpose times A transpose. If I factor transpose out, I reverse an order for the matrices. If I factor transpose out, I reverse an order for the matrices. So I write A first, then inverse of A. And here, A times inverse of A is identity matrix. And we know that identity transpose is identity itself. If both equations are true, then we know that inverse of A transpose is A inverse transpose. So the inverse of A transpose is this expression, A inverse transpose. Hence, the inverse of A transpose is A inverse transpose. Since the inverse of A transpose exists, then A transpose is also invertible. Hence, A transpose is invertible.